All right, so as I'm sure you're picking up by now, this chapter is everything to do with densities and how to manipulate them to find what we want that we knew from other physical examples, but this time in a more formal language. Again, this is if you have dreams of quantum field theory or any of the other field theories out there, you're definitely going to want to know these types of languages. So great intro in my opinion. All right, so for this question, we studied that in example 8.4, suppose that instead of turning off the magnetic field by reducing the current, we turn off the electric field by connecting a weakly conducting radial spoke between the cylinders. From the magnetic force on the current in the spoke, determine the total angular momentum delivered to the cylinders as they discharge. They are now rigidly connected so they can rotate together. Okay, good idea there. Now compare the initial angular momentum stored in the field, L equal -1/2 mu naught NIQ, big R squared minus little a squared Z hat. Okay, so let's go ahead and draw this out. The example in the book gave this diagram. You see we're rotating, current is running clockwise, it looks like, to the Z-axis, big R with some little a inside, positive Q inside, negative Q outside. All right, you get the idea here. Rotating in the fiat direction. Let's go ahead and walk it through. You see here, now since we have the momentum density, the linear momentum density, mind you, we also have the angular momentum density by taking a cross product of the momentum density and the radial component. So a lot of cross products, but nothing unexpected. This angular momentum is definitely going to, come back to haunt you again or excite you in quantum mechanics. So be ready for it. All right. So let's start. The solution is, since this is a solenoid in effect, again, quasi-static approximation, all that stuff still holds. We know that B is equal to mu naught Ni Z inside, or where S is less than R, and 0 outside. So the angular momentum can be found from the torque. Okay, now let's be very careful here. We just said that we could find the momentum from the density, but there's two different things we're looking for. We're looking for the force-generated momentum and then the field-generated momentum. So here we're dealing with the force first. So L is equal to the integral for time of the torque. Okay, remember torque is to angular rotation, what force is to linear movement. So since force yields to a change in momentum, torque leads to a change in angular momentum. Okay, a little flashback to mechanics there. All right, whatever. But we see that the torque here is the integral of R cross dF, so whatever the change in force is. Again, remember that torque was R cross F, and now we have it in the integral formation. All right, so let's move forward. Our dF is from the magnetic force on the current, which we know is I prime dl cross B. We've seen a bunch in chapter 5. So let's go ahead and run it through. We see that the dl is ds s hat cross the field, which is mu naught ni z hat. And if we remember from our cross products, we know what z cross s is, that goes to phi, but in order to switch them, because cross products are anti-commutative, we have to put a negative sign there, hence the negative you see. So let's go ahead and run it through. With that, now we have to find the torque cross product, which is s cross phi. Notice that I prime, U, N, and I are all constants, so shove them out to the front of the integral. And we see that S cross phi is equal to Z. Okay, so we get back to what we started with in the magnetic field direction. And then we just integrate forward. So that is ds, and we get a S squared over 2 from R to A. And what do you have? When you evaluate that, factor out of 1/2, you get negative 1/2 I prime mu naught ni r squared minus a squared in the z hat direction. And if we integrate that with respect to time, sure enough, all we're left with is big L with the I prime current, because that's the one we're discarding over. So that's what we get to Q with. And then as you see, we end up with the same angular momentum as we would have in the example. So that's pretty consistent. We like to see that. And remember, that's the mechanical force perspective. Soon we'll see what it means to be from the electromagnetic field perspective. Pretty cool.